Welcome to Matematika. Today we're going to do problems and solutions of polynomial functions and rates of change. We'll start with question 1. The graph of a quartic polynomial is shown on the left side. Question A, identify the zeros of g of x. Remember, the zeros coincide with the x-intercept on the graph, okay? Coincide the x-intercept on the graph. So let's say we have this point right here. It coincide the graph, this point, and this point, okay? So these are the zeros. We have 3, okay? So the zeros are what? When x is at -4, we have when x is at 0, and when x is at 2. Okay. The 0, we have the 0 which the x equals 0 has, remember, it has a multiplicity of 2. Remember in your algebra 2, sometimes we call it as double 0. What does multiplicity of a 0 means? That the number of times a particular value, our value here is 0, appear as a root when the polynomial is factored. Okay? Because it can be a root together with a value in the y-axis or a root of the value in the x-axis. That's why it has a multiplicity of 2. Label, letter B, label all local maxima and minima. Remember, local can be another term for relative. In the previous video we have. So we can find, if we try local maxima and minima, if we try to look at this curve, I had it marked already. At this point here, in A, point in B, and a point in C. Okay. When we say local, that's the time when the graph change from increasing or decreasing to increasing, and increasing to decreasing, switch. So at this point, we have this, because we have a decreasing here and change to increasing. At this point, it decrease and then change to increasing. Remember, we have a positive infinity here at this end. That's very important to know because we'll be using that for the interval later on. Okay. Label all the maxima and minima. So local maxima and minima are the turning point, as I said. Okay, I will write it down again. Local maxima and minima are the turning point of the graph. So when we say, as I've said, I've shown somewhere here, it tries to decrease, increase, then decrease, then increase. Okay? So at point A, let's look at point A. Right here. So where is point A located? Not exactly at -3, but somewhat almost at -3, somewhere here. Closer to -3. All right. And then how about in the y value? It's not at 4, it's not at 5, but it's somewhat in the middle, right here. So let's say we'll estimate, we'll approximate. So this, let's say this is in the middle, 4.5, and the x value is somewhat like a negative 2.9. Wait, let's blow this up. Okay, to make it clear. All right, like that. So the point A is a local minimum. It's local minimum. So I'll mark this as local minimum. So where is the approximately the coordinates? Coordinates are the x is somewhat negative 2.9 and the y is negative 4.5 approximately. If these things happen, always say the word approximate, because you're just estimating where the point is located. So we'll have the point B. Point B, you could say that the point B is a local maximum. Look at this portion right there. You see top of the hill. It goes like that right here. So I say that's a local maximum at the coordinates of, you're quite sure of the coordinates. That's 0, 0. Point C, that is when it turns again, and it's somewhat like you can see a curvature and you can see it's concave up. We have a concave up, concave down, and a concave up, right? So at point C, it's local minimum. At so we try to approximate because it's not exactly on the dot. So if we try to look at this one here, we estimate this point, and the x is somewhat like, is it in the middle of 1 and 2? So maybe not exactly, because it's much closer than the left of the 1.5. So let's say x is 1.4. And the y is much closer, somewhere here, somewhat in the middle or more than. So let's say a negative 0.7. Okay, I'm just approximating this. So I could say the coordinate is positive 1.4 and a negative 0.7. That's how, if you look at the graph and we are trying to estimate the location of the graph. Okay. Letter C is asking label all the global maxima and minima. So I said global is absolute, like global. Another term for that is absolute. Okay. So when can you say at the highest or at the lowest point? Highest or at the lowest point. So if we will look at all the local extrema we identified in this part right here, we have the minimum and maximum. Determine if any of them has the highest or the lowest points of the entire function. So if we say this point is not the lowest, also this point right here, but this is the lowest. Okay, point A global extrema, because it is the lowest function value in the global. So far from here, so low. Okay, so in other words, we have only one point, only this point A is a global or an absolute extrema. Because what the reason would be? Because it is the lowest point, or it has the lowest point. Say it has the lowest point, or you could say the lowest function. I would use the word function value. So the value of the function, then it is a global minimum. All right. Is the leading coefficient of g of x positive or negative? Now, take note, we are not given a function here. If we start from number 1, number 2, a letter B, letter C, the function is not given, but we are given the graph. Okay? So, how do we determine whether it's positive or negative? We should know, the first thing, know the degree. Okay, what's the degree? Then know the leading coefficient. Because if you know these two, then you can find the end behavior. So we could tell the end behavior here. Okay? And also the end behavior. Okay, we know that the end behavior are all positive infinity. Okay, they are all positive because it's facing up, on and on and on and on. So, basing on the leading coefficient, based on the degree and based on the function, the function has an even degree of 4. How do we know? It says in the beginning it's quartic. Okay. Quartic right here. Graph of a quartic. Okay. How do we know it's a quartic? It's positive. It is, both of them are facing up. How many turns do we have? 1, 2, 3, 4. Right? So the degree, the function, we could tell it's quartic, has an even degree. And what is our degree? The degree of 4. Okay? And both ends pointing at toward the positive infinity, as I've said. So the leading coefficient is positive by looking at the end behavior. Okay, so that means the leading coefficient is positive right there. Okay, we've answered. Or by just looking at the the end behavior, you could tell that the leading coefficient is positive. But I'm just explaining, like, in case it's not given, or it's not, there's an arrow in the end. So you have to be sure that it tells you the direction or the end behavior. All right. Number 2, the graph of p of x is shown. Okay. Identify the point of inflection of p of x. If we try to look at the graph, okay, let's go back to the definition of point of inflection. When does it occur? When the point of inflection. If you try to answer, always write it down. When you do a test or exam, write it down, look at the term that leads you to have your answer in the question. So point of inflection occur at where the concavity, remember, where the concavity change, okay, of the graph change or changes. Let's say from concave down, go concave up, then concave down again. So at that point, when it starts to change, there is a point of inflection. So if we look at this graph, there is a concave up here. At this point, there is a small concave down, and there is a small, and it suddenly have a concave up. So that means there are two set of changes is happening in this graph. So where is that point of inflection happening? Okay, we could say to the left. There is another. We can see that there is a point at exactly 2, 4 right here. From down to up. Okay. What else could we see? A point of inflection from up going down, so somewhere here. At this point, suddenly it changes. Okay. So point of inflection occur at this point and also at this point. Okay, so I would identify one point of inflection at this is 2 and 4 in y, so at 2, 4, and the other one a point of inflection occurs somewhere, let's say somewhere here. That is before going to 1 and at this point. So we can make this point. I could make this point right here. Because when I intersect, it goes exactly here. So that's one point of inflection. So before going to 1, I could estimate that as 0.8 and 2. So 0.8 at x and 2 in y. That is where we approximately, because I don't have an exactly amount of value of the x at point 8. So describe the concavity of the graph. So let's say, for example, somewhere here, we have the, the point of inflection. So inflection 1, inflection 2. Okay, let's describe the concavity. The concavity, remember, changes at a point of inflection. So we can use the point of inflection to divide the graph into section. So I could make this as 1 up, and this is where it went down. The concavity is down, and somewhere here the concavity is up. So actually, there are 3 parts or section in the concavity. Okay? Let's say to the left of the concavity, this is negative, this is positive infinity, right? Okay, this is positive infinity. This is negative infinity for x. This is positive infinity. This is also positive infinity since this is going up. I have a negative infinity for x. I need that because our end of the concavity is, infinity. So the left and the right are concave up. So I mark it here. And only one concave down is at the, at the middle. So in the concave up, let's have the interval. As I've said, this is a 0.8 up to here. And I made that as an approximation. So I'll have an interval of a negative infinity for x value, and for the y, okay, I'll start the concave up here. I have a 2 and a 0.8. Okay? And another concave up, and another concave up when it is at 2, and going up it's positive infinity. Okay, going up here. For concave down, we have only one concave down. So I have here a 0.8 and a 2 for concave down right here. From here, this is the interval. From there to there, it's concave down. And 2 to infinity, this is concave up. And from here, negative infinity to 0.8, that's another concave up. All right, I think those are the important information that we need. So if you use a function notation here in concave up, you can have function notation like combine. You use that, and 2 and 8 and infinity, I mean. Using the function notation. 3. For each of the following polynomials, determine if there is an absolute minimum, absolute maximum, or neither of that. We are talking about global extrema here. First, we need to know the leading coefficient or the degree. That's what is the important there. Okay? Once you know the degree and the leading coefficient, then you will know whether you have an absolute minimum or maximum or none. So if we look at the given in A, it's a factored form of a polynomial. It's a factored form. It's not straight having the higher degree down to the degree of 0. All right? So what we're going to do, we don't need to expand fully. But we know that when we multiply 3x times x, we know that we can have a 3x squared. We don't need to multiply 3x times 5 because our target here is to find the degree. And this x raised to the second power is also an x squared. All right, so remember the rules of exponent. When you multiply, you add the exponent, right? So our degree here, the degree is 4. So it's even. All right, it goes with the rules of the absolute extrema. And the leading coefficient is positive. Okay, even positive. That means the arrow goes up at both ends. So we have what we have here, a minimum. All right. So we have here an absolute. Okay, we'll try to expand. Absolute minimum. Okay. Same thing here. Let's look at the degree. Remember, we have a negative leading coefficient. So it's still in a factored form. So that would be 4x to the third power, then raised to the second x to the second. So what do we have here? A negative 4x to the fifth power. Remember, this is odd. So there is no global or absolute extrema here. So it's none or neither, none. Either of that. H of x is x squared minus 6x squared minus 2x to the fourth. So let's look at this highest degree here. We have x to the fourth and also this one. That's x to the second power. Then negative x to the fourth. We add the exponent and it has a negative. So even degree, negative coefficient, that means it's both ends are facing down. So that means this is your maxima. Right? So we have an absolute maximum. Here. If you are somewhat like confused, this is really confusing, class. I mean, everyone. Sorry for that. I made a class again. This is really confusing about knowing the maximum and minimum, especially when it's global. You have to check where is the direction of, the arrow or the infinity, if both are facing down or facing up. So when it's down, you have a maximum. When it's facing up, you have a minimum. Okay, we have that notes. Go over to the notes we had in my previous video, then you can check upon it. Okay, so this, and for now, and what I can say, if I can do it, so can you. Will you hit the like button and also the subscribe? Hit the subscribe. If you haven't subscribed yet, please do. Thank you. See you in my next video.